Thank you once again. Now we will be concentrating on our blast research, and here emphasis will be placed on retrofitting and strengthening existing buildings. And recent research at University of Ottawa involves reinforced concrete columns as being one of the critical elements. Concrete slabs and walls, these are one-way and two-way slabs. Masonry walls, as was mentioned earlier, masonry is used quite extensively, although we don't like unreinforced masonry. Fact of life is that they are used extensively. And there's timber stud wall research as well, and windows as being one of the most vulnerable elements, and then there are other protection systems. I'd like to show you, first of all, the research facility that we have. In our blast research lab, we have a shock tube, which can go up to 15 psi, which is about 100 kPa, and the duration can be up to 50 milliseconds. And the shock tube consists of 3 segments. First of all, the driver section here, which looks like a long pipe, and this is where we charge the shock tube. We put compressed air. There are no explosives to detonate, but it's simply compressed air. And then we have spool section, which is a short steel cylinder, and then there are 2 aluminum diaphragms placed with different capacities. And so they balance the pressure. The one on the driver's side has higher capacity, the other one has lower capacity, but the balance keeps them in the difference is balanced, so that it is not triggered until we want to trigger it. When we want to trigger it, we release the pressure within the spool section, so then the pressure drop exceeds the capacity, and then at that instant we have a blast phenomena taking place, and aluminum diaphragm punctures, and then at supersonic velocity, shock wave moves towards this expansion section. Now, expansion section is shaped this way in order to generate uniform pressure. Right? Otherwise, there will be higher pressure in the middle and lower pressure at the ends, but this enables uniform pressure, and this is a 2 meter by 2 meter test area where we can put columns, beams, and panels. And this is the kind of shock wave we typically get. This is the duration, this is the reflected pressure, and the area under this curve is impulse, so area keeps increasing. Blue curve gives impulse, red curve gives pressure time distribution. I will show you the results of, very quickly, of course, some of our experimental research projects. This one involves FRP. This is carbon fiber polymer, and in order to strengthen column capacity, we have as build column without strengthening, and then with jacketing. Jacketing means hitting fibers in the transverse direction. And then we wanted to increase capacity by providing longitudinal fibers, which then worked as longitudinal reinforcement. But then there was debonding issue, and a surface bonded FRP always has that kind of a problem. And then we used longitudinal as well as transverse fibers, which gave the best result. We did develop bond equation under high strain rate. So typically at a strain of 0.009, debonding occurred. So if you want to design, it's not the fiber capacity, it was the bond capacity that covered. But when we used transverse and longitudinal fibers, we were able to rupture the fibers, which means bond failure was prevented. And here you see longitudinal fibers ruptured because we first put longitudinal CFRP and then transverse CFRP, which confined it. Here you see comparisons. These are pressure time curve as well as displacement time curve. So these are the displacements. So red one is as built. So under same pressure, this is the pressure distribution here. Under same pressure, we got 80 millimeter deflection And when we put longitudinal fibers which suffered from bond failure, it reduced down to 65. And then when we put confinement, it reduced to 45. And then when we used both, it came out to be 35 millimeters. So gradually, by using FRP, we were able to increase capacity. And then we also tried another retrofit technique, which is called RetroBelt. We had originally developed a RetroBelt system for seismic retrofitting, which involves transverse pre-stressing of columns. As you know, when you provide transverse reinforcement, you provide passive confinement pressure to concrete. Concrete capacity goes up, concrete activity goes up. But we developed this technique in which we provide active pressure by essentially squeezing concrete in transverse direction, unlike conventional use of pre-stressing, which is in the longitudinal direction. So we did the same, and we also covered columns with precast concrete pieces to increase its mass. So we get the double benefit of higher mass and confined concrete. And we use, because these columns have relatively small diameter, when we applied it for seismic applications for bridges, we used 7-wire pre-stressing strands to pre-stress them in transverse direction. But in this case, we used high steel packaging straps having 800 MPa strength. We also tried lateral bracing system and either tension or compression brace. For compression brace, we again had to put precast concrete units and then tie them with packaging straps to prevent buckling. Here is compression brace, the way it's working. And then we had tension brace, as you can see, providing lateral support. These braces are supposed to be anchored to top and bottom floors. And the same column without retrofitting, of course, fails in a drastic way. So retrofitting with lateral bracing proves to work. So if you have critical facilities or critical infrastructure where columns are at risk, you can either use FRP or you can use this kind of lateral bracing. And then we did analytical research for close-in and contact charges. Our facility does not permit close-in simulation of close-in explosions. Therefore, we did finite element analysis. We used Elastina, and we looked at performance of columns. So here, if the explosives are placed close to the column after half a millisecond, 2 milliseconds, and then eventually it failed at 14 milliseconds by spalling of concrete. Now, when we put 2 kilogram backpack bomb at 1.5, the other one was at 0.5, there is somewhat improvement, but still material failure dominated rather than member failure. And then we looked at wall panels by taking strip of a continuous wall. These are one-way wall panels. We again tried using FRP, and we had bond failure. As you can see, as built specimen was able to resist 43 kPa, retrofitted under 73 kPa pressure, it failed. And then we had another specimen at 80 kPa with failure of the bond failure of FRP. So what we did was we then developed anchors for FRP so that they would not debond. Here is the homemade anchors made out of carbon fibers. So we attached them to the ends to keep them in place so that under blast they would develop their full tensile capacity. And we were able to eventually get higher strength. And here's the video of fibers FRP without the anchors. As you can see, it freed itself from the bottom. What you see is aluminum foil coming out of the shock tube, and that's the load application device simulating uniformly distributed load. And then, but when we used fibers, as you can see, anchors were able to keep them in place, and hence capacity went up. So here's the comparison of capacity. green line shows